afternoon, everyone. Today, the Atom Seminar has the great pleasure to welcome Professor Dill. He received his bachelor and master's degree from the Department of Mechanical Engineering at MIT. Then he obtained his PhD from the Department of Biology at the University of California. And later he worked at Stanford University as a postdoc researcher, where he studied the cellular structures by focusing on the structural dynamics of micelles. Professor Dill is a biophysicist and chemist best known for his work in folding pathways of proteins. Professor Dill's main research interests include computational modeling of proteins, development of theory and computer simulations on protein folding, and understanding cell behavior. He is the director of the Louise and Beatrice Lofer Center for Physical and Quantitative Biology at Stony Brook University. He was elected a member of the National Academy of Sciences in 2008. He was also elected to the American Academy of Arts and Sciences in 2014 and has been the editor of the Annual Review of Biophysics since 2013. So once again, welcome Professor Dill. Thank you so much for being here, and please feel free to start your presentation.
Thank you very much. Thanks for the invitation, and thank you for having me here. Let me start by sharing my screen. Does that work? Does everybody see a single screen?
Not yet, Professor.
No? Okay, hang on a second then. Let me try it again. Does that work?
Not yet, at least not for me.
No, not yet. No.
Oh my goodness. Okay. Well, let's see.
Here you go.
Yes.
Now
coming.
we have it.
Yes.
Great. That's working. Okay. Terrific. Terrific.
Yes.
Sorry about that. Okay. So let me begin here. So what I want to tell you about is trying to model water in a different way than explicit solvation or implicit solvation. I'm coming from a background where we like to think about simulating biomolecules, and currently the way you do that is by mostly molecular dynamics, either with explicit or implicit simulation. But I'm thinking, 30, 40, 50 years from now, when we simulate cells and whole big, huge complexes of proteins, we don't want to be wiggling waters around. And we want something that's both fast and physical. And so we've started on this sort of a Don Quixote kind of trail here, tilting at windmills to see if we could build something. And that's what the story I want to tell you. It's a progress report. We don't have a grand scheme of things yet, but we're sort of trying to get there. So we call it Rocketwater. And what I mean, all I mean by Rocketwater is just we want something super, super fast. We're trying to make it essentially as analytical as we can. And we're pretty close on the 2 or 3 areas that I'm going to tell you about. So this is the sort of thing we care about, is thinking about, okay, molecular water properties. Let's see, you can see my, okay. Never mind, my pointer isn't working. On the left in the picture, you can see a tetrahedral water molecule, and on the right, you see macroscopic properties. The question is, how do I go from microscopic structure to macro properties? Why do we care? All the standard things that you all know at least as well as I do: biomolecules, drugs, materials, polymers, non-covalent chemistries, things like that. Liquid water has these anomalous properties, as you all know, density maximum and so forth, and various features listed here. And what we'd like to see is for that to come from a model. And that is not only an interesting sort of statistical physics model, but also can capture properties fairly accurately for us. That's our 2 objectives: are super fast on the one hand and accurate enough to capture properties, a sort of a chem engineer's approach, you might say here. We try to keep it as physical as possible, but we have parameters every once in a while. So here's the idea for us. What is a better computational model of liquid water? It would be as physical as an explicit solvent model, like a tip 3 piece kind of model, for example, but as fast as implicit solvent but hopefully better physics than the implicit solvent. A brief history, I'm pretty sure, is not needed here at all, but I want to frame this in terms of not molecular dynamics simulations per se, but also in terms of the kinds of models that other people have thought about, some analytical, some lattice simulations, and so forth. Where's the history of sort of the roots of this thing? So going back to van der Waals and so forth are the earliest models, I think, thinking about liquids as spheres, and having that spherical symmetry is very powerful and useful in statistical physics kinds of averaging. And then you have the Weeks, Chandler, and Anderson model. Then for doing that's then going beyond liquids like argon was liquid water, and so the roots of that I think go back to at least Bernal and Fowler, Röntgen even before that, dipolar spheres, the Stillinger model, which is a 6-point water model, very expensive to run, but it's still pretty good. And then all the TIP models and the SPC models and so on came around in the 80s and 90s. I do want to mention a recent analytical, not quite analytical, but an expansion model, sort of in the spirit of where we're headed here, which is by Valeria Molinaro. But in the mid 1990s, when we were doing a lot of modeling of proteins using simple models of proteins and coarse graining and so forth, we were thinking more and more about how do we get the water part as accurately as we possibly could. And in the 90s, so we started the work that I'm going to describe to you now in the 1990s, but at that time, we felt that there were a number of unmet needs. And what I mean by that is molecular dynamics simulations were then being used for water-like models and argon and so forth. But the difficulty is that it was not meeting a need for speed. And by speed, I mean computational efficiency. For example, you couldn't compute an entire temperature, pressure, phase diagram over the entire liquid range of water in a reasonable amount of time. You could do a 1 point or 2 at a time, and you would typically do 1 atmosphere pressure and typically room temperature. Certainly in biology, those are the only things people care much about. But broader than biology, we would like to know phase diagrams. Couldn't do ensembles. That's very problematic for water, because ensembles, it's not just single water molecules and even water pairs that are interesting. It's the structure of water. It's the cagey-like nature of water that we wanted to capture, and we weren't seeing that very well done in the 90s. In MD simulations, you couldn't really get entropies very well. You couldn't get cage structures. You couldn't see heat capacities. Hard to simulate, a lot of noise, and so on. And interpretability, that what I mean by that is that when you do trajectory-based modeling, molecular dynamics, for example, your inferences are very noisy. You see one trajectory, you see another, you don't really know exactly what's the message and what's the average versus what's the variation from the trajectory. Analytical models are nice because you have a very straight thread from the model itself all the way to whatever inference you want to draw without having extra noise come in. So mid 90s. So we decided, okay, we were going to do some self-education. We were going to just fool around with some little toy models for a while and see if we could learn how to deal with some of those problems. And it's been a long road, but I think we did learn some things. And then the learnings we got, we now put into some analytical models. So we have this thing we call the Mercedesbenz model. Show it to you in a second. We did a bunch of different kinds of integral equation approaches with a group in Slovenia. This is Vojko Vlachi, and now Barbara Hribar-Lee is heading up that group. We've collaborated with them a long time. And then we also do some fictitious solutes. I'll show you what I mean by that. Here's the Mercedes-Benz model. It's a 2-dimensional thing. We call it Mercedes-Benz for obvious reasons. It's the logo. It's got 3 arms. And so instead of water being 3-dimensional and tetrahedral, it's 2-dimensional. It's got 3 arms. Arms can be either donors or acceptors for hydrogen bonds. We don't distinguish in this model. This was not our idea. It was first done by Ben Naim back in 1971. I think he thought of it as a way of teaching high school kids about water. And we were looking around at, we looked at a ton of models at that time. There were lattice models and so forth. trying to see what we could learn from. And the bottom line is we ended up with this model and we just loved it. It's got just a lot of great features for learning and doing so very quickly in a computer about various properties that are quite water-like. I'll show you in a second. But here's what it is. It's a potential function that is a 612 potential in distance. These two disks have a 612 potential in distance. And the hydrogen bond is a Gaussian function. So it's when two arms of two different water molecules are lined up, the Gaussian is at its peak. It's the strongest, that's the biggest population. And then it gets weaker. It's a sort of a Gaussians are spring-like forces. And so it gives you a spring-like variation. And we did this in NPT Monte Carlo and we studied it like crazy. And there was, because you can do a lot with a model that's this simple in a computer. So these are qualitative pictures, but this is the sort of thing that you get on the right side is a picture of the volume per molecule of water. So flip it upside down, it gives you the density. So it shows you a density maximum right after you get past the freezing point as you go to the right. The thermal expansion, the heat capacity, isothermal compressibility, and so on. Experiments are shown on the right. The two-dimensional MB model shown on the left. Of course, I can't compare them in the same units because dimensionalities are different and so on, and it's a qualitative model. But the gist of a lot of the features, if you stare at this a bit, you see a lot of the features are basically there, not all quite as quantitative as we'd like. But the implication to us was, gee, well, if we could do this now in 3 dimensions with tetrahedra, I bet we could even do maybe a little better. Here's what we learned over that period of time, mid-90s to a decade or so later. First of all, the complexity that really screws you up in trying to get a better, faster model of water is that you have two totally different symmetries and they're incompatible. One is you have to deal with the tetrahedra and the other is you have to deal with spheres. That doesn't work very well in most models. And so we needed a way, what we learned from these models was you needed a way to understand that incompatibility. A lot of people would then, in StatMech models, would resort to saying, well, let's assume water is just spherical and so on. But we recognize that that wouldn't be sufficient, really. You can't capture all the properties. You can't get structure to properties that way. 2 dimensions is often okay. We learned this in proteins too. We could make 2-dimensional models there. You can often capture the physics reasonably well. It's simple, and the problem is that you don't get quantitative answers, but at least it gives you physical dependencies. Cages matter a lot. So even in liquid water, of course, in ice, you have sort of nothing but lots of water cages. But the thing is, when you're in very cold water, down just around the freezing point, you have lots of very cagey-like structures in water. And if you don't capture those, you miss the essence of cold water. What we found was not essential a distinction to go structure properties is whether you have donors and acceptors. So our concept of just an arm is an arm, and if they line up, that's great, was sufficient for a lot of things. Obviously, if you're doing pH studies, this kind of model doesn't work. And the other thing is you have to go beyond the pairwise interactions. And this is work we did with Tony Hammett back then in the 90s. Bottom line is if you do a rigorous entropy expansion, what you discover is you don't even get the right sign for liquid water for its entropy until you get to the 3-body terms. And if you have and so you need something that's better than just a low order expansion. These are the things we felt we learned. And then, so these are the things we then said, let's see if we can build an analytical model that captures these features and still gives us speed and might give us some accuracy. So rolling the tape now forward, this is 2018, just a couple of years ago. This was the model that we assembled from all of that. So I'm showing in the top line here the partition function, and I'm showing it to you in a little sort of cartoony set of pictures. And down below are the 3-dimensional versions of what we're capturing here. So the model's 3-dimensional, but the picture is just to illustrate so you can see what we're trying to explain here. So the first term, the blue picture, Mercedesbenz molecule picture, is indicating that, okay, I need sometimes I have monomers. So it's something like a low order expansion. I have to have a monomer term. And that means, and especially when you get, for example, if you were to go to the gas phase, then that's most of what you would need. Then we have two body terms. One is the hydrogen bonding, and that's the one that's shown with the two arms lined up. And then a non-hydrogen bonding where you have just the van der Waals interaction. So those are the two body terms. Now, when I say term, what I mean is we have to integrate over all the stuff that works. So a hydrogen bond, we integrate over the Gaussian functions. Or in a van der Waals case, we integrate over everything that's not hydrogen bonded. So these are kind of mesoscopic terms, if you will. You have to do some integrating to be able to get what is the whole hydrogen bonding story, if you want that, for example. And then here's where we deviate from kind of the standard thing, and that is one body term, okay, fine, two body terms, okay, fine, and then one 15 body term. It's a, sorry, 12 body term, 15 bonds. 12 bodies is because you have the cage, a water cage in ice is like two benzene rings stacked on top of each other. So you have 12 water molecules that are all bonding together, and then you have 3 bonds across the two, and that gives you 15 hydrogen bonds. And so we have a 1 body term, 2 body terms, and 1 12 body term, if you will. So rather than doing a low order expansion, the idea is water is a very structured liquid, and you need something in your partition function that captures that. And we just skipped over everything in the middle. Now, to do this right, of course, ultimately you might want to fill in more in the middle, but this has worked out fairly well for us, I would say. I'm going to show you the results in a second. First, just briefly, these are kind of what the terms look like. They are analytical, and the reason is because you're integrating Gaussian functions. So the top, the hydrogen bonding term is an error function. I'm just integrating a Gaussian function here, and so forth. And there's a pressure volume term for the monomers and so forth. And down at the bottom is the partition function that sums over all the things that can happen. Each of those delta terms is itself an integral over what are the options that allow that particular object to exist. And this stuff is really fast. You can compute all of it. So this is what you get. What we cared about, as I say, what were 2 things. One is we wanted this to be as analytical as possible, and this one is. Those are 4 terms. All the integrals are ones that have closed form terms, and so if I want to know heat capacities and so on, I just take a derivative of the partition function with respect to these various things. Now, this is showing you a comparison of the modeling over, so the x-axis here is the temperature range from the freezing point. Sorry, it goes from below the freezing point because I also wanted to show the supercooling water result. But you see the first tick to the right at the bottom is 0 degrees, and then it goes up to 100. So it's a liquid water range plus some supercooling on the left. And the orange deltas are experimental data points. The black curve is our calculation, and the blue dots are showing you tip 3P water. What you can see is, first of all, tip 3P water doesn't do very well. It doesn't give you the density max, for example. It's pretty noisy, and it also is off a bit in some of these properties like thermal expansion. But this cage water model does pretty well. Now, this is not adjustable parameter free, but it does have, but it's basically physics. And then we have some volume terms, and we need some parameters there. So we did have to adjust those. But you don't have, there are no simulations here. These are calculations. And so we can get this whole liquid range in, on a CPU in a few minutes. And so the accuracy is, not showing in here, but you can do it. The accuracy is about the same as tip 4P 2005, which is what people regard these days as the standard for simulating pure liquid water. Tip 3P is too few points. 3P indicating it's a 3-point model. You need to go to the 4-point model in tip 4P if you want to get things like a density max in a simulational explicit solvent model. But of course, as you go up the series into more and more points, it gets more expensive. And then what we're aiming for here is something that's not expensive at all. So we can do temperature, pressure, phase diagrams, and we can do supercooling. You can see at the bottom the heat capacity. It as you go below zero, the heat capacity does rise like it's supposed to do. What the experiments show is you get this supercooling peak. I'm not going to spend much time on the supercooling thing, except one thing to say is that a lot of simulations in recent years from the DeBenedetti group and the Chandler group, for example, were looking at supercooling, and often where you run into trouble is that those are simulations, they're molecular dynamics, and when you go into very cold water, everything gets kinetically stuck. And if you're looking for, is there a double minimum for supercooling in the free energy, or a single minimum, that is, are there two liquid states or not, which has been one of the big questions, you can't really tell, and it's dependent on the water model. You can't tell because the barriers are high and the minima have about the same depth. It's very difficult, and a simulational model in principle is not the ideal way to go. In the analytical model, you can draw direct inferences because you don't have that kind of noise, and we can go down to any temperature we want. And the bottom line is you do see two minima. You do see two liquid states, basically. This is a picture that just shows over the temperature range from pretty cold, zero is in the middle now, pretty cold all the way up to the boiling point. The top plot is showing you what our calculations show in terms of our terms. We have the four terms. We have the monomer term, we have hydrogen bonded pairs, we have van der Waals bonded pairs, and then we have cages. And those are our four terms, and we can look at the populations of them over temperature, and what you see is in very cold water, everything is cages. The cages melt out, and by the time you get to the freezing, or let's call it the melting point, by the time you get to the melting point, now what happens is a lot of the cages have broken and you've got lots of pairwise hydrogen bonds. Oops, sorry. Lots of pairwise hydrogen bonds. And the van der Waals contacts start growing in at higher temperatures, and the cages by then have all disappeared. And down at the bottom, I'm just showing you, this is an IR study of water. This is from Luck in 1998. Just indicating he sees three peaks, and those three peaks are kind of interpretable in terms of the quantities that we calculate. So the black curve could well be sort of the hydrogen bonded bits. The blue curve could well be the van der Waals contacting bits, and so forth. So we can make connections at this level, if you will, with some experiments. So here's a little cartoony way of thinking that we like to think about water. On the left is sort of a standard picture of an energy level diagram, if you will. And the lowest energy level is when you have a material as a solid, think of argon or something. Then you heat the system up, and what happens is you populate higher energy levels. And so now that's less dense and it's looser and more disordered. Of course, that's liquid. Then you get to the gas phase where the density is very low. Now, so on the right, I'm showing you what the picture is that emerges from all of this, from this model of water. And of course, you get cagey structures in ice. What happens is you get broken cagey structures in cold water. Then in hot water, you really have very much a van der Waals kind of liquid. Very few of the hydrogen bonds are there anymore. And those that are there are not contributing much. And then finally steam up here. And the main point for me to show you this picture is to show you this density quirkiness. Low density in ice, still lowish density in cold water, higher density in hot water, and lower density in steam. And that's all consistent going all the way back to Röntgen in 1898, who argued, hey, water is a little weird. If you look at the density and its weirdness, you can think of its weirdness in first approximation, as he did, just curve fitting data, as it having water being a two density liquid. And that's what we get to, is basically the low density is the cagey structures, and some of them are still left in cold water. And then when you melt them out, the density goes up. So this is showing the components. This is helpful to us because it's a way of interpreting what's going on with water in structural terms. And by structural terms in this case, I mean our four components to our partition function. So you see again, the orange points are the experimental data, and the black curve is showing you the total heat capacity. In this case, we're doing a heat capacity calculation. And what we're doing is the breakdown of heat capacity in terms of its components. What you see is the agreement with data is pretty good. And now the question is, well, okay, where's that coming from? What are the microscopics here? Well, the blue is showing you the cages. In very cold water, this is now supercooled region, it's nothing but cages. And that's really what's giving you that supercooling peak. You're basically melting out cages before you ever get to zero. And what you're melting them out to is broken cages. And then that's what you see here. And as the cages break more and more, you go more from a hydrogen bonded liquid to a van der Waals liquid. Also, we can calculate pressure effects. This is also pretty quick. Mostly we don't get any new insights we didn't have before. Squeezing crunches out cages and turns them into more, it pushes from being a hydrogen bonded liquid to a van der Waals liquid. So it squeezes the solid into a liquid. That's, everybody knows this because we all teach PChem about ice skating and stuff like that. So now what I want to tell you about is solvation. So now I want to try to take this kind of model and I want to put solutes in it. So everybody knows that water is a universal solvent. It's almost a universal solvent. It dissolves everything except your kids. And so the question is, how do we think about water as a solvent? So this is the sort of general picture. I have some kind of a nonpolar solute, that's the sphere, and it's, let's say it starts in oil and we're transferring it to water. So this picture has been around really a long time, ever since data has been available, and that goes pretty far back, you know, before the 1940s, even with Frank and Evans. And the gist of the idea is from A through C, let's think about cold water. It's very hydrogen bonded, very cagey. I now have, with no solute in it, now I insert, whoops, sorry, keep doing that. Insert a solute, and now what does it do? It structures water into these cage structures. But what happens if I now go into hot water is that those hydrogen bonds are no longer really dominating the system anymore. A lot of them are broken. And so now the solute goes in, it's dealing with a structure of water in the first shell that's not nearly as cage-like. So we model this. We call this the Crust water model. This is also a Rocketwater model in the sense that it's very much, first of all, it's based on the cage water model I just mentioned. The model I just mentioned is only for pure liquid. It's pure water, nothing in it. And now we're trying to insert a solute into this. And crust water, the term is simply because we're dealing with this first solvation shell here, and we just call it a crust. So what is the water structure around a solute? And so you could say, if you look at implicit and explicit, you could say, well, explicit is particulate water, not crust water, because every molecule you have individually that you look at them individually, or you could call implicit solvation, you could call it smeared water or something like that. In our case, we're not smearing the water. We're actually thinking about them as tetrahedra, but we're integrating over some stuff. We're not actually taking each water molecule one at a time. And what are we integrating over? Okay, so let me tell you what happens when we stick a solute into our cage water model. So cage water, the model I just mentioned, is still the background. It's still what the bulk is doing. It's exactly what the bulk is doing. We just take the bulk as being nothing different than I just showed you. But now what happens when I have a solute? Well, I have a couple of things going on. And in particular, two of the most important ones are, here's my, let's see, sorry, can I, oh, can't do that. Okay, so the orange thing underneath the two waters is a solute. And the left picture at the top is showing you a hydrogen bonded structure of two waters in the crust. And that's what the system would most like to do energetically and entropically is the rest of the story here. So, but what happens is you have some orientational freedom. And that orientational freedom means what I could do if I was a water molecule is I could point one of my hydrogen bonding arms straight at the solute. That's the red arm in this picture on the right side. That's not a good idea, especially in at low temperatures, because that arm is going to waste a hydrogen bond. So what it really wants to do is be the picture on the top left. That's the dominant population. And the question is, well, what's the cost then when this thing rotates down and points the wrong way? And this is work of, this is very recent. This is work we're just finishing up right now. This is my three collaborators, Pradipta and Ajit are in India, and Vigeli Koutsias is here at Stony Brook. And Vigeli did a brilliant piece of work in analytical treatment of how to think about all of these water conformations analytically, sitting around a solute of any radius. Always spheres, but of any radius. Okay, orientations are the top two pictures. I rotate a water molecule, but it's sitting next to a solute. And then there's translations too. And they do tend to correlate a little bit, but the idea is the distance between a water molecule and the solute also matters, and it's an entropy as well. And it's not a hydrogen bonding pairing entropy, it's a sort of a density entropy. So the 4 bullet points on the left are the summary of what we're doing, what we're adding to the cage model. We're dealing only with the first solvation shell in this problem. We deal with the orientational entropy, which says that the solute is geometrically a problem, and we compute that. Translational entropy is all about the looseness of packing, and we have a term for that as well. And then, of course, there's an energetic interaction between the solute and the waters. And the bottom image here is just showing that the delta G, what we calculate is the ratio of the two partition functions. The one on the top is the hydration shell, it's the crust, and the one on the bottom is the bulk. And by taking that difference, now what we get is the solvation. And again, our aim here is both speed and predictive accuracy at trying to get experimental data. This is showing you 3 inert gases. We've done the other inert gases, but it's too much to put on a single figure. And then we have benzene and methane, and also showing you the top line is the free energy of solvation. The second line is the enthalpy. Third line is minus T delta S. Fourth line is the heat capacity. Modelos reasonably well. You can see it's not perfect, but it does reasonably well. Now, it also does reasonably well versus TIP 4P 2005. Again, this would be what we would consider to be kind of the gold standard from molecular dynamics simulations with explicit solvent. And the picture on the left is our calculation of xenon, TIP 4P calculation of xenon, and then CH4. And these are simulations. The TIP 4P modeling was done by Peter Cummings' group. What you can see are the 3 things: the experiments, the TIP 4P, and the crust water. So this is a model where the predictions for what we are able to calculate are about at the level of TIP 4P. Now, we can go back into the model from all of this, and we can interpret what's going on. What is solvation? What's the solvation physics in terms of the quantities that I mentioned before? And this breakdown, sorry, you can't see it too well at the bottom. Let me just interpret it for you. The interpretation is really the 4 yellow bullet points here. In cold water, where you have a lot of KG-like structures, the enthalpy is favorable. And this is fairly straightforward. It's that the solute and the water are attracting each other. And now, so what happens, and so what's the entropy? Well, the entropy is that you're caging, it has tight packing, that's unfavorable. This is sort of the classic hydrophobic effect, the creation of cages. Hot water is interesting because the hot water, as you heat, the dominance moves from solute water terms to the water terms, and now it's all about the shell. It's about the water hydrogen bonds, and so the enthalpy goes up as you heat because you're breaking hydrogen bonds. You're crumpling your crust, and the entropy goes down. The minus T delta S goes down. Becomes more favorable in the delta G terms. because your water-water bonding is getting less restricted. So this is a point having to do with the free energy per unit area. There was a nice paper by Lum, Chandler, and Weeks in 1999 in which they said, hey, let's plot the delta G divided by the area of a solute. I'm transferring a solute, again, doing the same thing, transferring a solute into water. I pick some temperature, let's say. In this case, I think it was 298 was where we took the data. Anyway, the picture on the right is showing you the Lum, Chandler, Weeks prediction from their 99 paper, and we made a prediction right after that, different physics. So the Lum, Chandler, Weeks physics is all about fluctuations, and are they important and so forth, and do you have water fluctuations at surfaces? Our physics was more or less the same one that I've just been describing. It's the hydrogen bonding orientations and translation, not in the fluctuations per se, but in the mean values. The two models led to pretty different predictions, and at the time there wasn't data to really look at. So Lum, Chandler, and Weeks basically said this was a nanoscale effect, and that you would, first let me just tell you what this picture is showing you. As a function of the solute radius, what happens is this: you see a change in the free energy divided by area, and then it gets flat. So the reason it gets flat is because now you have a surface area effect. When you're large solutes, the bigger solute you make, the more surface area you have, the more water structuring you're dealing with. So it's just a surface area effect. Everybody's been using this kind of idea for years and years, that grow a solute, and now it means more surface area with the water, and that's costly. And the plateau values in both of these old models had to do with, okay, how costly is it when you do that? But the dip down on the left was interesting, because this is saying if I have a solute that's smaller than a cage, teeny little solute, and I stick it in a cage and I grow it a little bit, the cage doesn't know about it. The cage is the cage. The smallest cage that water molecules can make is of a size that can roughly hold a water molecule inside it. And if I have some molecule or atom inert gas that's smaller than a water molecule, then I can grow it, but the water shell doesn't know about that. So there's no surface area effect until you get to a certain size where the solute now pushes against stuff. And Lum, Chandler, and Weeks said that was true for their model of fluctuations, and we found that was true also for our model, which just says solutes grow and then they start pushing on the cage. The difference between the two models was the LCW model said it happens, the crossover happens around 10 or 20 angstroms, and our model said it happens around 1 or 2 angstroms or so. Now, with our current model, and now with current data, we have a lot more information to go on, and the data on the left is showing you, I think black is the 6 or 7 inert gases, and the blue is the small non-inert gas molecules. And what you see is you do see these effects. The top line is the free energy of insertion. Neither of us before Lum or us thought about enthalpies and entropies, but they exist now. The information is available now. And what you can see is the crossover is around an angstrom. So I think that's telling us that this is what the physics is. Really small solutes. The cage doesn't really much care until you get to a size where the solute is big enough that it starts really pushing on the cage. I'm going to briefly skip that in the interest of time and finish with a next step. And this is where we are in this next step at the moment, is that Pradipta and Ajit have been working now also on charged solutes, so ions, for example. We have, what I just showed you was only non-polar and only spheres and only simple and small. At the end of the day, if we're ever going to build some kind of a machinery that's going to be useful for solvation, especially in biomolecules or materials or chemistry or what have you, it's going to have to deal with all kinds of different solute sizes and shapes in chemistry. And so we have a long ways to go. But the next step is to try to do something with charges. And so how do we do this? So first, I'm putting up here the 3 bullet points that are here are a summary before I show you the results of what are our main conclusions about what needs to be in a model. Now, this is from toy model studies, and this is what we are trying to learn in order to get something into building a model. First of all, very important, water has an electric dipole that's off center. And what I mean by off, well, I'll show you that in just a second and a little more clearly in a slide. Secondly, small ions solvate very strongly because the electrostatic fields are strong. And third, negative ions solvate more strongly than positive ones. Let me just make that case. Here's the toy version of looking at experimental data. Now we take water molecule again, looks like this Mercedesbenz thing, except now there's a dipole moment in it. A -1 where the oxygen is in real water. In a three-dimensional, tetrahedral water, the oxygen is pretty close to the center. And the hydrogens where the plus end of the dipole is sit pretty close to the surface. So the dipole is not centered where the mass center of the water molecule is. The dipole is off center. The -1 is at the center. The +1 is out near the edge. And that has a big effect on how you deal with solvation of ions. And so this, we think, is one principle that's really crucial. And I'll show you results on that. So for example, one thing is the size of an ion. How does the size of an ion affect its control over a neighboring water molecule? Well, I'm showing the top green thing is a small ion like lithium, and the bottom is showing you a much bigger ion like a potassium, for example, or cesium is huge. So this is showing you two different ion sizes. It's showing you that ion ordering a water molecule, and what it does is it drives the water to point its dipole away from the plus charge. This is for plus charges, for cations. But on the right side, what you see is a distribution function that's showing you that if I have a little ion like lithium, it really grabs a hold of water very tightly and does not allow water to do much because the ion has an electrostatic potential that's so close to the water molecule that it's very strong. Bottom is showing you normal electrostatic potential, drop off 1/r kind of thing. And so if I have a small ion, I have a very strong electrostatic interaction. Bigger ion, less control over the water, if you will. So also there's an asymmetry here as well, and the picture on the right shows that. Suppose I have a small cation, the green plus charge, or I have a large anion, which is the orange or something, orange or yellow minus charge. The thing is that there is an asymmetry between plus and minus, between cations and anions. It's been known a long time experimentally, but it's because the water dipole is off center. So if I have a plus charge, it's going to drive the water to point its dipole away. If I have a minus charge, it's going to drive water to point its dipole towards. And now the thing that's crucial is what is the distance between the ion center and the closest charge on the water dipole. And so you can see that picture on the right, and you can see the consequence of that on the figure on the left. These are data that have come down since the 1930s or so, indicating certain ions are called cosmotropes and certain are chaotropes. This one, by various measures, that's true. And this happens to be the entropy. And what you see is two things from this figure on the left. First is, as you go from small ions to large, look at the blue line with the red dots on it. This is all cations, or look at the red line with the anion series. And you see small ion like lithium, top left, really orders water a lot. Cesium at the bottom disorders water. That's just the picture I was showing you a second ago. And that's true also for anions, except the whole anion series is offset. So bigger anion like fluoride, which is about the same size as potassium cation, have very different effects of ordering versus disordering, and that's because of this water dipole effect. Now, so at curved surfaces, it has consequences, and a model needs to think about this stuff. Implicit models don't. Explicit models do. So the picture on the left shows you, suppose, and so I'm making stuff up here. Suppose what I do is I have a little hill, the gray beads are nonpolar, and I have a little plus charge inside there. And I'm going to bring a minus charge from through the water up to that hill, the peak point on the hill. Now, implicit solvent would say, I don't really care whether you have a plus charge in the hill and a minus charge in the water or the other way around, it's all the same. There's total charge symmetry. And yet in real water, in explicit water, you capture the difference, the important difference, which is that dipoles, water dipoles aren't symmetrical. And so in fact, it turns out if you ask, what is the stable state? If I look at a negative ion in water coming up to a plus ion versus a positive ion in water coming up to a negative ion, the stable state on the right is the contact pair, and the stable state on the left is the solvent separated pair. So if you wouldn't capture this unless you have water's asymmetrical dipole in the model. And this is, here we're making stuff up here. We're inventing some molecules. And this is, we call these turtles. And so my turtle, the blue turtle on the top right is that I have a benzene ring. Let's call it a benzene ring. It's 6 beads. And I'm going to invent some charge. So I put a -1 at the head group, the turtle's head, and I put a bunch of plus 0.2s. So the thing is net neutral, but it's got a dipole moment. And the bottom is just flipped around the other way. It's the dipole moment now with a plus charge on the head and the minus on all the tails. Well, it turns out the sense in which we make this up is we put these charges on beads and we run tip 3P simulations and we stick them in water and we ask what is the solvation free energy of putting the red-headed turtle into water versus the blue-headed turtle into water. What is the difference? Well, of course, in the implicit, there is no difference. It's perfectly symmetrical. In explicit water, the difference is 10 kilocalories for that one little molecule. And so that's huge. So this asymmetry in water is not some third order effect. This can dominate kind of everything. Let me skip this one and show you the last few slides I want to show you are how water orders differently around ions of different sizes and charge. And all of this, these are all things we've been exploring in these toy models because we ultimately want to know what physics do we need to be putting into a more analytical version. So let's look at this one first. So if I have a plus charge for picture on the left, I have a like lithium, let's say, a very small plus charge. What it's going to do is it's going to hornswoggle. It's going to control the first shell waters, the light green ones, by driving the dipoles of those waters to point outward. You can see those 3 light green waters have dipoles all pointed outwards. These are situations where lithium is so small that its electrostatic field is so strong that it's the dipole interactions that are driving what water is doing, not hydrogen bonding. So water is getting ordered by a lithium, but it's getting ordered by an electrostatic mechanism. Now I get a bigger, in the middle is a bigger one. I put and it's also negatively charged. So I have now a fluoride, and in that case it's negative. And so now you see it's a small ion also, but it's an anion in this case. It's now driving waters to structure electrostatically too, but they're pointing the dipoles at the fluoride rather than away. And finally, when you get to something big, either iodide, which is negative, or cesium, which is positive, now the charge density is low because the ion itself is pretty big. So the charge that the waters see is pretty small. And in this case, interestingly, when you get to large ions, doesn't matter which sign, they just look like hydrophobic solutes. So water orders now by hydrogen bonding. You can see a little bit of hydrogen bonded structure around the iodide. So the size and charge determine, am I driving this by a small plus ion to point dipoles away, by a small negative ion to point dipoles toward, or a large ion of either side, which is basically just leading to the hydrogen bonded structure, like just a normal hydrophobe would do. That we need to capture too. So the Hofmeister effect is really interesting. There's a Hofmeister effect in which essentially what happens is small ions look like they're big and big ions look like they're small. What I mean by that is there's a sort of an inverse volume effect. Now the gold thing is showing a nonpolar solute. So this is a Hofmeister effect. What is it? So this is a case where I have three things in a beaker. I have water, that's dominant, that's a solvent. I have a nonpolar solute, and I have some ions, some kind or another. So it's well known, goes back to Hofmeister in late 1800s. It's well known that what happens is ions will affect by a lot the solvation of a nonpolar solute. You can have salting in or you can have salting out. And the question is, what are these size effects? And so here, this is a little sort of cartoony picture of this. What it's showing is that when I have a small ion, it strongly interacts with the first shell of water, and the nonpolar solute can't actually get into that first shell. So the little ion looks like a big ion because it's got so strongly got a solvation shell around it that the nonpolar solute is just totally excluded. On the other hand, when I have to the right, on the right side, on the other hand, when I have something big like an iodide, like I mentioned, that's hydrophobic looking itself to water. And so it's happy to associate with a nonpolar solute. And therefore, iodide looks like just the size of iodide, simply because, and as far as the nonpolar solvation is concerned, they're happy to interact with each other. They look to water, they both look like nonpolar solutes. And so this accounts for this inverse correlation of size effects. Let me just skip that, get to the end here since my time is about up. This is the summary. What we've been trying to do is to learn from all kinds of models, toy models, two-dimensional models, Mercedesbenz. We also have done a bunch of integral equation modeling on these models. I didn't show you much of that stuff. We make up these fake solutes where we can do systematic series and put them into tip 3P water to see what tip 3P water thinks they look like these turtle calculations we did, solvation of turtles and stuff. So we try to learn from those things, what is water like in ways that might be missing from MD simulations or ways that we could capture in analytical modeling. We do 2 dimensions first. That's a very quick and simple and very intuitive and visual way to test the physics. And when we think that it's looking like we got the right physics, then we go into 3 dimensions, we do tetrahedra, and then we try to see if we can match experimental data. For nonpolars, the point I made with the crust water model is that hydrogen bonds break either as you increase the temperature or as you increase the solute radius. So there's a sort of a mapping here. A big solute is very much like hot water in a certain way because they have the same effect on the first solvation shell. And finally, the last point we've done one paper on this. Pradipta and Ajit have done a very nice paper on this in 2 dimensions. So our first step for ions and off-center dipoles. And the Slovenian group also had done this through Mercedesbenz-like simulations with a dipole in it. What's clear from the modeling is that off-center dipoles are really crucial to capture in a water model. And that ion radii and the charge also control the strengths. And these are the people that did the work. Tomasz Urbich was the one who did cage water. Ajit and Pradipta have been the ones who've been doing solvation. Vigeli is the one who solved analytically. He's our applied math gunslinger, and he's the one who solved the analytical treatments of how tetrahedra, all the ways tetrahedra can sit around the solute. Kevin and Barbara and Emiliano and Chris have done some of the earlier work on the simplified models, and Marivi, and thank you all for listening.
So Professor Dill, thank you so much for the presentation. We are now open to questions. If you want to ask one, please enable your microphone or write it down at the chat. We will read it. And also our YouTube viewers can write it down, of course.
Can I start?
Sure, go ahead, Professor Fred.
I have two questions. Thank you, Ken, for this very nice presentation and exciting. So I'm going to study more your papers about these waters, cage water. My question is two questions. One is how this cage water model predicts or calculates critical points.
Okay, yes. So at the moment, we've only done liquid state. So in order to get things like critical points, for example, what's needed, and actually for all the other phase boundaries too, for that matter, we're going to need a model of the solid, a model of the gas, things like that. So we have in our simulations, in our Mercedesbenz model simulations, we have found transition points that we can, we think we can assign to something like a boiling point, for example. And but at this moment, I don't have any three-dimensional results because I also we haven't gone to the trouble of trying to model the solid and the gas phase yet.
Thanks. So the other question is, how could you can we compare this model with SAFT type model? In SAFT, like for C model, you cannot form exactly cluster kind of this cluster that you have shown, but somehow we form kind of 3D clusters. If we have kind of 4P models or for C models.
Yeah, that's a good question. We have not looked at that. We really have avoided looking at the SAFT models so far, not for any particular good reason, but just mostly because we haven't gotten around to it. It would be a good idea. Thanks for that.
Thanks.
Thank you. Thank you, Professor Fred, for your question. Professor Carol Hall raised her hand. Please feel free to enable your microphone and ask your question.
So Ken, where do you think you will eventually go on this? Am I going to be able to use a package that has your implicit solvent model to fold proteins or to do something like that, or that's not your goal?
Yeah, that is our goal. Something like that is very much exactly where we're headed with this. And so as I see it, there's a potential bifurcation. Either we crash and burn somewhere and then it all dies, or what happens is we get towards something like a package. Now, so what does that mean? What do we need to do next? There's a ton of things we have to do before we know if we're going to crash and burn or not. One is small spherical solutes is not sufficient. So we have to go to things that are more complicated in shapes. Begaley is trying to work his magic on dealing with that at the moment on, first of all, the dumbbell, the sort of die things and so forth. Second, we have done a thing called the seawater model before, where we did learn some useful things too. And that tells us how to make additivity relations. So if I have a big complicated surface, a bunch of pluses and minuses and nonpolars and things like that, I think we know now how to do additivities over the surface. And the gist of it is that the problem with additivity is if you do anything that's smaller than the size of a water molecule itself, you're really stuck, because hydrogen bonding in waters means you get correlations that go 3 waters away. And so additivity doesn't work if I try to do it for something like an argon size. I need to integrate more. We learned this from the seawater model. We're going to need to learn how to do this integration thing in the modeling that I'm talking about. So one is complicated shapes. 2 is how to get something like additivity relationships over bigger sizes. 3rd is how to get charges. And who knows what we're going to crash into in doing that. But that's exactly what we are aiming for. You're absolutely on the nose here.
Great. Can't wait.
Yeah, it'll be a few years.
Okay.
Thank you, Professor Carol, for your question. Professor Richard has sent a question through the chat. Please, if you are in the audience, feel free to enable your microphone, Professor Richard, and ask the question.
Okay. So Bennett Marshall has been experimenting with water models too, and he's shown some similar results in terms of the anomalies and representing those. His model approaches it from a wartime theory perspective, and a couple of features that he's added. So with second order TPT, you can include 2 bonds to one site. And so I think he's added that. And another thing is there's a tendency for, if I'm remembering this right, if once you've already formed one hydrogen bond, then it somehow helps the next hydrogen bond to form. And I think he found that that was necessary. And so he's put that together, and that was what gave him this ability to represent these anomalies. So I thought that was pretty interesting. And then I was just wondering, have you tried anything like that and then you ruled it out for some reason that I don't know, or have you just not looked at it?
Yeah, great question. Yes, we have. We've done a lot of work with Wertheim models, mostly some with water, some with just with just water solutions. But most of what we have used Wertheim modeling for is protein-protein interactions, and there it's been very helpful. It's because Wertheim is so good at dealing with strongly associating liquids. That's essentially what it's built to do. And so you can combine the levels as well. This is our Slovenian group that's been doing a lot of this work. You can combine the levels. So you could do water is sticky and proteins are sticky and maybe ions, I want ions and stuff. I could, in principle, nothing prevents you in the Wertheim world from doing, all of those levels together if you wanted to. We've done a few of them sort of together. We haven't explored it all that much. Coming back to your second point, though, I would say, we find exactly the same thing. It's this cooperativity term is absolutely essential. Now, in our case, and one of the differences, by the way, is that the reason we haven't gone to a lot of Wertheim modeling for all the things I've talked about here is that Wertheim costs you some computational time. This stuff costs you nothing. This is just essentially zero computational cost. That's why I really like going this direction, because at the end of the day, I want to be able to solvate whole cells, or I don't know, crazy stuff, really big things. And I just don't want to have to spend my computational time on water. I want to spend it on interesting stuff. Anyway, but the point about cooperativity is that we include that in our cage term. So when we have in essence, what we have is a single water and the 2 pair terms, the hydrogen bond and the van der Waals bonded terms. And those are normal in the sense that there's a hydrogen bond energy and there's a van der Waals bond energy. In the cage, we have a cooperativity component. So the hydrogen bonds are stronger. Our cage hydrogen bonds are stronger than they are in the pair. We can't get the liquid behavior without that. And what I think is it is real. I totally take your point and his point that it is real. I think you need real cooperativity in a real water model, especially in cold water. You have to have something like that. And of course, if I look at the simulational models, Explicit, for example, you typically have just 2-body terms. So it's a way in which I think even though our model is highly simplified, it does capture an effect that really is true in the higher order physics if you had it in there. I think we got to have it.
Could I ask one quick follow-up?
Sure.
Sure. So you mentioned something about the computational cost of Wertheim's method. So is that because you have to solve this big matrix of equations for the extents of hydrogen bonding, those mole fractions not bonded? That's where the cost is going?
Yeah, and I don't mean to say that it's super expensive. It's certainly cheaper than doing something by pure simulations. Absolutely. What I mean to say here is we're trying to get to Rocketwater. We really want to be blazingly fast. That's the main thing.
Okay, I think I understand. Thank you very much.
Yeah. Yes.
Thank you. We have another question in the chat. So Professor Raja, feel free to enable your microphone and ask the question yourself.
Thank you, Professor Dill. Thank you for a wonderful talk. Can you make some comments about solutes like small neutron molecules like oxygen, nitrogen, and hydrogen peroxide and urea, something like that? Will this water model work for these substances?
I don't know. We haven't tried it. It's a good idea, and it's a very nice direction to go. It's sort of the thing that would be next on our list to do, because we are trying to get to something that's not pure spheres, but still reasonably nonpolar, maybe has a dipole in it, things like that. Carbon monoxide, another case, for example. Great direction, and it's sort of the next step, but I don't have anything I can tell you about at the moment on that.
Thank you, Professor.
Let's see if we have any more questions.
Miguel Jorge.
Hi, hello.
Okay.
So I was just wondering if, I mean, obviously this is all very interesting. I'm just wondering if you looked at interfacial properties, sort of maybe like interfacial tension between water and alkanes, or, you know, I suppose if you're wanting to go for cells and stuff like that, you probably want to look at interfaces that are bigger. Would this work there as well?
I think it would. There's a very interesting old problem that goes all the way back to Hildebrand and Tanford. They battled over this, I don't know, 50 years ago or something, which has to do with why is it that if I take something small like benzene and put it into water and I calculate something like an free energy of doing that per unit area, and then I compare that to the interfacial tension between liquid benzene and liquid water, there's a factor of 3 difference. Ballpark is 25 calories per mole per square angstrom for little things, 75 calories per mole per square angstrom for big things. Why is that true? So yes, we can do that. And so in our case, what we do is we would just grow the radius of a solute. We can do that, no problem. We can put in even as a function, we can look at the full temperature dependence of everything as a function of radius. And you do see the effect. Basically, where it's coming from is that small solutes are often, if they're small enough, they're compatible with a nice hydrogen bonded cage of water, and water is very happy keeping its cage if it could, and cold water. But that by the time you grow your solute pretty big, what happens is this: I'm starting in cold water with a small solute. My waters are just great because they're very happy with all their hydrogen bonds. When I make the solute bigger and bigger, what happens entropically, what happens is the decision that has to get made is, okay, I got to waste a hydrogen bond. I got to waste at least 1 hydrogen bond. What do? I waste it the best way I possibly can. I just point it straight at the solute. That way I get the other 2 really well. And that's the difference in the cost, basically. That's the threefold difference. So yes, we can. We've not done very much with it beyond that, just to say sort of here's what that difference is. But I mean, in principle, that's really where a model like this, I think, could potentially be useful, is to think about lots of interfacial kinds of properties, maybe different interfacial chemistries and so on. One thing I think would be really fun would be to think about dynamics and diffusion, for example, putting water molecules through nanopores and nanotubes and so on. They seem to zip right through. And that presumably is because they don't get stuck bonding to anything on the walls. But trying to do that, do the diffusion and calculate rates and stuff like that, I think that would be super interesting. We haven't done any of that sort of thing yet.
Yeah, maybe I can ask another quick question. Have you thought about using a hybrid approach? You know, somewhere where you have a few water molecules that are discrete, and then the rest is this coarse-grained rocket water. Would that work as well? Because that might be interesting in, you know, sort of like pocket reactions or something like that, wouldn't it?
Yeah, it's a great idea. I hope that's a plan B. What I really hope is that plan A works, which is to say we don't have to do that because we don't want the expense. And so like every time Vigeli comes back and says, oh, I can do something where I can do a little calculation. I got a, you got a complicated surface, I can do a calculation. We always say, no, Vigeli, go back to the drawing board and get us something analytical. And he's been great so far.
Thank you. So our time is almost over. I want to thank everyone for the discussion. And once again, thank you, Professor Dill, for the presentation.